Hello viewers, I am Kausalya. Today we are going to see the derivation of generalized error coefficients, otherwise known as dynamic error coefficients. As we all know, the formula for error signal is given by E of s equal to R of s by 1 plus G of s into H of s. So here I am dividing this numerator and denominator into two separate parts. So 1 divided by 1 plus G of s into H of s multiplied by this R of s. Now this term is replaced by the letter F of s. Right. So E of s can be written as E of s is equal to F of s into R of s. That is this term is represented here as F of s. That's it. Then, as we all know, when we take inverse Laplace transform of E of s is nothing but E of t. F of s is nothing but F of t, and Laplace inverse of R of s is R of t. Right. Now we are going to introduce a new theorem that is known as convolution theorem. That is, by convolution theorem, inverse Laplace of f of s into r of s can be written as integral of minus infinity to plus infinity f of t into r of t minus t into dt, right? This is a convolution theorem. By convolution theorem, we can write f of s into r of s like this, right? So, we know f of s into r of s is nothing but this f of s into r of s is nothing but E of s, right? So in the next step, I am replacing this f of s into r of s as E of s. And as we all know, inverse Laplace of E of s is nothing but it is our E of t. So E of t is equal to, again here when you see the limits, here minus infinity to plus infinity. As we all know, whenever we are giving an input signal, the signal always exists or starts from 0. It won't exist beyond 0. That is, no negative signal is allowed. So here in this case, so that is the reason here why we are changing the limit as integral of 0 to infinity. Right, because no signal exists below 0, that is no negative signal. So here we are changing our limit to 0 to infinity. So f of t remaining r of t minus t into dt, it remains the same, right? So mark this one as equation number 2. And the next thing we are going to use Taylor series. Okay, these are all the max terms. Hope you heard all these terms already. So using this Taylor series expansion, here what we are doing is we are expanding the term, that is r of t minus t, we are expanding using this Taylor series. So what is this Taylor series? Here we have expanded, you see, that is r of t minus t is equal to r of t minus this capital T into r dot of t. R dot is nothing but differentiation, right? Plus t square by 2 factorial into r double dot of t, and again minus t cube by 3 factorial all triple dot of t, plus it goes on, right? So here the main thing to be noted is first one is with positive sign and next one is with negative sign, and it goes like this, again plus, again minus, like that. Right. So as we all know, r dot of t is nothing but when you differentiate r of t for the first time, that gives r dot of t. When you differentiate r of t twice, 2 times, then that gives r double dot of t. Right. Now mark this expression as equation number 3, and here we are having our equation number 2. The next step is we are going to substitute this 3 in equation number 2. That is, instead of r of t minus t, I am going to substitute this expression. Right. Here I have substituted the values. That is, E of t is equal to integral of 0 to infinity f of t. Instead of r of t minus t, I have substituted this entire expression, and again finally we are having this dt. Right. Now I am going to multiply this f of t inside this bracket. So here we will be having f of t into r of t into here dt. Right. Minus integral of again 0 to infinity f of t into r dot of t into dt. I am bringing this f of t and this dt inside. Right. Both are happening together, plus again f of t into, you see, t square by 2 factorial or double dot of t into dt, like that. Just this is a simple multiplication, right? I am moving this f of t as well as this dt inside the each term, present inside the each term, right? So here I am having the expression like this, that is I am having each term has its own integration and each term has its own dt and f of t, as we have multiplied in the previous step, right? And the next thing is, when you look carefully here, you see we are going to integrate this f of t with respect to dt, right? And here this r of t is a constant here, because I am going to integrate this expression with respect to this dt. Since here we are using capital T, we are going to integrate f of t with respect to dt. Here r of t is a constant. It is just like a number, right? So here the next step is we are going to take that r of t term outside, as these are constants. Hope you people understand why I am saying r of t as constant here, right? So the next thing is, as I said, since r of t is constant, I am taking r of t outside. So the remaining terms will be integral of 0 to infinity f of t dt. Similarly, here r dot of t is taken out, and here r double dot of t, and here r triple dot of t, like that, right? And our expression ends like this. And finally, now we are going to replace this integral of 0 to infinity f of t into dt by a single term. We are going to replace just for our convenient. So here, you see, in the place of here, this is our first thing, right? So 0 to infinity f of t into dt is replaced by c naught. Similarly, 0 to infinity t into f of t into dt is replaced by c1. Again here I am having minus sign, so I am considering this minus sign also. And the next thing for again c2, 0 to infinity t square into f of t into dt, right? And for c3 again minus integral of 0 to infinity t3 into f of t into dt, and finally it goes, so cn is equal to minus 1 to the power n integral of 0 to infinity tn f of t into dt. So finally, we are going to replace this integral term by this c0, c1, c3, cn, etc. So when we replace the term here, we will be having, you see, e of t is equal to r of t into, instead of integral 0 to infinity f of t into dt, I am writing as c1. And similarly here, sorry, c0, and here c1, c2, c3, and it goes on. Right. So this is our final expression for generalized error coefficients. So here the generalized error coefficients is given by, here e of t is equal to, just I am rearranged, c0 r of t plus c1 r dot of t plus c2 by 2 factorial r double dot of t, and it goes on, right? So here we are saying that c0, c1, c2 up to cn are known as generalized error coefficients, right? So finally we had come to the end of this derivation. Hope you people understand. Thank you.